about modeling of the structure and dynamics of the DNA hydration shell. So please, Tatiana, you can start.
Thank you. Thank you very much for the introduction and good morning for everyone. So the first funny thing that I have unstable internet connection in the university. So it might be that in some point it crashed, but let's hope for the best. So yeah, today I want to tell you a little bit about the structure and dynamics of the DNA ion hydration shell, and here is the short outline of my talk. So I want to once more remind you about the DNA structure, but it will be super fast, I promise. And then I'll go to tell you about the role of water and ions in the helix formation, a little bit about the structural and dynamical features of the DNA hydration shell, and also I would like to tell you a bit about our recent work regarding the vibrational dynamics of ion hydration shell using the molecular dynamics method. So let me start shortly from the beginning, from the structure of the DNA macromolecule. So as you all well know, that the DNA is a biological macromolecule, and it plays a crucial role in the all living organisms. So DNA consists of the two polynucleotide chains that run in opposite directions and twisting around each other to form the double helix. So the basic unit of the DNA structure is the nucleotide, and it consists of the three groups: the phosphate group, sugar ring, and also nitrogenous base. So the phosphate group and the sugar ring, they form the DNA backbone. Sorry, can you hear me? Because there is something going on with the internet.
Very well.
Yes, we can hear you perfectly.
Okay, thank you very much. So yes, the phosphate group and the sugar ring, they form the backbone, which is placed outside of the double helix, and the phosphate group, they are negatively charged, while the nitrogenous bases, they are hydrophobic and they're hidden inside of the double helix. Usually, the nitrogenous bases, they come in four types. It's adenine, thymine, guanine, and cytosine. So adenine pair, thymine, guanine pair, cytosine through the complementary hydrogen bonding. The surface of DNA, as you can see, is not uniform, and the minor and major also groups, they can be distinguished. And it's well known nowadays that under the physiological conditions, DNA surrounded by water molecules and ions, which actually plays a crucial role in the structural organization and the stability of the DNA double helix. And starting from the very first X-ray and the modeling studies, it was clear that the water and ions, they influence the DNA structure. On the slide, as an example, you can see two different X-ray diffraction patterns, which was taken by Franklin and Gosling in early 50s. So what they did, they exposed DNA to two different humidity levels. And let's say in the dry air, they saw that DNA become shorter and, let's say, thicker, producing this sharp and scatter pattern. While in the moisture air, DNA stretched out and the pattern changed to this clear X shape. So this showed that DNA can exist at least in the two conformation or two forms. It's a form on the left of the slide and the canonical B form on the right on the slide. That this later helped also to discover DNA structure by Watson and Crick. So the DNA double helix, it conforms when enough water molecules are presented around it. And nowadays, we know quite well how many water molecules are required to stabilize the double helix form in the given conformation, or let's say form once again. So interesting fact that the number of water molecules that are needed, it significantly depends on the type of ions which is present in the experimental sample. Here on the slide, you can see the images of the A and B form, which I took from the protein data bank. And in the table on the slide, you can see the summarized known data, where the sum list of alkali metal ions shown. It's lithium, sodium, potassium, rubidium, and cesium, and showing the condition of DNA. It's A or B form or the dry sample, and also the last column showing the relative humidity and the number of water molecules per base pairs, which are required to form the sum of this conformation of DNA. So in general, the B form of DNA typically requires about 90% of relative humidity, and this is about the 40 water molecules per base pair. While in the case of A form, it needs less. It's about 75% of humidity, and it's around 20 water molecules per base pair. So from this table, a clear trend can be seen. It's when ion larger, it reduces the number of water molecules which is needed for helix formation. But there is one exception, as always, and this exception is lithium ions. And you will see that lithium ion, it's always some exception. But nevertheless, despite the small size of this ion, it's effectively neutralizes the negative charges on DNA phosphate backbone, so the less number of water molecules are needed to stabilize DNA double helix. So DNA interacts strongly with the surrounded water molecules and ions and forms them around itself the ion hydration shell, which is running over the 80 angstroms from the DNA surface. This shell can be roughly divided into three layers or shells, where the outermost shell, it behaves more like a bulk water. Closer to DNA, the intermediate layer forms, or the second hydration shell, where water molecules, they do not make direct contacts with the DNA surface, but still influenced by the long-range non-bonded interactions. Also in this region, which is about 7 angstrom thick, the ion atmosphere forms or observed, which we are talking about a bit later. And the water molecules and ions that are in direct contact with the DNA atoms, they form the first hydration shell, and this part of the hydration shell is the most ordered, and inside the double helix in its grooves, the water molecules are even more ordered, and here water molecules in the major groove shown in a blue color, and in the minor groove the water molecules are highlighted in red. For example, the characteristic feature of the B form of the DNA is the formation of the relatively stable and ordered structure of water molecules in its minor groove, which is now known as the spine of the hydration. And the hydration spine was firstly observed by the Drew and Dickerson when they provided X-ray studies of the structure of the fragment of DNA with following sequences, which for now known as dodecamer of Drury-Dickerson. This figure I took from their original work from 1981. So what they show that in the case of the 80-rich minor group of the fragment, the water molecules, they can breach the nitrogen and oxygen atoms of the opposite strands of the bases of opposite strands of the DNA. As a result, such a structured ordered structure is formed in the minor group. These water molecules, let's say from the first layer, they can also make the contacts with the water molecules which surrounded them, and as a result, it is shown that in the minor group, some ribbon which is composed of the water hexagons are formed. This structure is not unique. For example, in the case of the R form, also the ordered structures of water molecules can form, but there they can form between the phosphate groups because of the short distance between these groups in the case of the R form. So for a very long time, it was believed that the DNA can structure water only in the case of its minor group, as we discussed before. But the recent studies using the experimental chiral sum frequency generation spectroscopy, which was also supported by molecular dynamic simulation, they showed that the DNA actually organizes water across the entire first hydration shell. This includes not only the minor group, but also major group and the water molecules which are localized near the phosphate groups of DNA. On the slide, you can see the results of MD simulation, which are agreed with the experimental data. Here you can see the DNA fragment, which is highlighted in yellow. The DNA put it in the water box, which water molecules here, all water molecules in the system, they are highlighted in black. And the water molecules from the first and the second hydration shell, they are highlighted in the red color and blue respectively. Here you can see the graph that shows the calculated sum frequency generation spectra for all water molecules in the system, as well for the first hydration shell and the second hydration shell with the corresponding color. You can see that the first hydration shell, which is red, it produced a strong signal similar to the total signal of the sum frequency generation response. It indicates that in this part of the hydration shell, the water molecules are well ordered, while in the second hydration shell, it shows almost no response. So what about the dynamics of the hydration shell? Its dynamics is also not uniform as its structure, and it depends on the position of water molecule within the hydration shell around the DNA. This is a very nice figure which shows that actually the hydration shell is a very dynamic formation, and water molecules can change their position within one hydration shell, which is indicated by the black arrows, and also there is the they can exchange water molecules between the different hydration shell around the DNA. So the numbers of the experimental and also the computational data show that the characteristic residence time of water molecules which are located in the bulk solution is about 1.5 picosecond. When in the closer proximity to DNA surface, the dynamics of water molecules, it's noticeably slowing down, and the characteristic residence time near the phosphate group, they are increased to the 10 picoseconds approximately, and the most slow water molecules are observed in the case of the major and minor groove, and while in the major groove it's around 100 picoseconds, in minor groove it can reach even 1 nanosecond. An important feature process for the water dynamics in the hydration shell as well as in the bulk solution, it's an exchange of hydrogen bonds which can happen when the water molecules reorient itself through the large jump or turn. And this reorientation mechanism is well described by the in the jump model, which was proposed by Lash and Guinness. I hope I correctly pronounce their names. Anyway, if you want to read more about this model, because it's super interesting, you can read in detail about it in these references, which I provided in the bottom of the slide. But let me just explain it schematically. Let's imagine that this black line, it's a DNA surface with some oxygen atom, which forming a hydrogen bond to some water molecule, let's say water molecule 1. When a new oxygen atom acceptor comes close to the first water molecule, let's call it water molecule 2, and stay at a distance approximately equal is the old partner, the water molecule OH group, it can jump between these two acceptors. And during the jump, it temporarily forms a bifurcated hydrogen bond with these two acceptors, creating such a transition metastable intermediate state. And the new hydrogen bond becomes stable once the old bond breaks. Of course, water molecules can jump either to the other water molecule or to atom of the surface of the DNA, but it was shown that the jumps between water molecules are especially important for the hydration dynamics. And also interesting thing that studies shown that the dynamics of water in and DNA double helix, they are interrelated, and in particular DNA conformational dynamics can speed up the motions of water molecules, and especially in the confinement region like a minor groove of the helix. So the also the reorientational times for water molecules were calculated, and results show that the water orientational times in the bulk water, it occurs in the time range between 1 and 5 picosecond, while closer to DNA near the phosphate groups, the time increases to around 10-30 picoseconds, and inside the DNA grooves, especially in its minor groove, reorientation slows down significantly with the time that can reach at about 80 picoseconds. So when we are studying the structuring and dynamics of water around DNA, it's also important to take into account the ions that are also present around the double helix. And as I mentioned it before, that around the DNA, the ion cloud is formed, and this was predicted in the early studies by simple polyelectrolyte models that was discussed yesterday during the Dr. Trieste talk. And later, this prediction, theoretical prediction, they have been confirmed also by experimental methods Here, as an example, I want to show you the results of the small angle X-ray scattering of the DNA in solution with different ions, which is listed in the figure. So here you can see in the black dashed line, they show the theoretical prediction, which is in the where they agreed well with the later experimental results. In general, the ion cloud around DNA actively studied using also molecular dynamic simulation. And here, as an example on the slide, some results from the MD also presented. In these studies, they studied the distribution of the sodium and chloride ions around the DNA fragment and the different concentration that you can see on the legend of the graph. So they show that in the case of these ions, sodium ions are found mainly near the DNA phosphate groups. Here, sorry, on the graph in the 0, the DNA axes are placed. Yes, they show that the largest density of the case of the sodium ions are found near the phosphate groups, while in the case of chloride ions, the density increase in the concentration further away, reaching the bulk levels at around the 30 angstrom from the DNA axis. Also, in the bottom graph, the meaning radius is indicated, which is predicted theoretical with the models, and it's actually indicate where about the 75 or 76% of the DNA charge is neutralized by ions. So they get the closed value to the predictions at about the 60, 70 angstrom from the DNA axis that agreed well, as I said, with the calculation. So regarding the ordering of ions around DNA, there is another example based on the MD simulation results for the DNA system with various ions. It's lithium, sodium, potassium, and cesium. In the graph, you can see the top-down view of DNA cross-section with the helix center positioned at 0 on the graph. And here also on the bottom graph, you can see the highlighted ion binding sites. In this site, the minor group, and in this side, the major group. So what they show that, for instance, in the concentration of lithium ions is the highest near the phosphate groups, while in the case of the potassium and cesium ions, they are predominantly found in the inner region of the double helix in its minor and major groups. Also, using the MD simulations, the residence time of counterions were calculated for the case of the different regions of the double helix. It's a minor group, major group, and phosphate groups. For some of the ions listed here, it's sodium, potassium, cesium, and magnesium. So the results show that ion dynamics in the minor group of the DNA double helix are significantly slower than in the other studied region. Sorry. In this way, the cesium ions have the longest average residence time, which can reach 1 nanoseconds and showed as a green line, while the sodium ions have the shortest residence times around 100 picosecond and showed as a black line. In other regions of the double helix, the residence time are much shorter than in the major group, and for example, in the major group, the longest residence time observed for the case of the cesium ion and the magnesium ions also, and it's approximately 200 picoseconds. Close to a phosphate group, the residence time were found under 400 picoseconds, following this order with the longest residence time in the case of magnesium ions and the shortest time in the case of cesium ions. So the interaction of the counterions with DNA strongly depends on the type of ion and particularly on its hydration properties. And counterions in the solution, they can either disturb or stabilize the hydrogen bond network of water molecules around them. And based on how water molecules organized around the ion, the counterions can be classified as either as structure-making or as structure-breaking ions. The structure-making ions, such as lithium, sodium, or magnesium, they have ordered water molecules in their hydration shell compared to the bulk water. So typically, these ions interact with the DNA indirectly through the water molecules in their hydration shells, since the dehydration is the energetically cost process. In contrast, the structure breaking ions, they have more loosely organized hydration shells than even the bulk water, so they can easily get rid of the water molecules and squeeze into inner region of the double helix. In this case, an important factor influencing the strength of the interaction of ions with the surrounded water molecules is the ion charge density, and ions with the higher charge density, they create a stronger electrostatic field, which results in more effective attraction of the surrounding water molecules. So also the using the molecular dynamics simulation, the residence time or dynamics of the water around ions was studied. Here on the slide on the left, you can see the results for the ions in bulk water solution. One can see that in the case of the structure making ions, the residence time of water molecules can reach the 10 tenths of the picoseconds, which indicate the ordered and structured hydration shells, while in the case of the structure breaking ions, the typical residence time of the water molecules in their hydration shell is about the 7 picoseconds. That is less than in the case of structure making. That indicates the more dynamical and less structured hydration shell. But also the interesting thing that another study, molecular dynamic study for dynamics of water molecules around the ions. It specifically was studied the sodium, potassium, and cesium in the different regions of the double helix. It's a minor, major region, phosphate groups, and it was compared to the bulk results. It was shown that the residence time of water molecules around the ions, which is located in the inner regions of the double helix and especially in its minor group, they obtained that residence time is much higher compared to the bulk water solution. So where we go next, knowing all this data. So we can see that the structure and dynamics of the DNA, water, and ions, they are closely interrelated. And the one way to better understand, one of the way to better understand this complex system, that study its vibrational dynamics. Since the vibrational spectra, it can capture the characteristic modes of DNA, water, and also ions, and therefore it serves as a powerful tool for probing the structure and also dynamics of ion hydration shell. So in particular, the vibrational dynamics of ion near the phosphate groups of DNA were studied within the framework of the dynamic ion phosphate lattice model, which was explained very well yesterday by Dr. Prepelitsa. It was shown that the ion phosphate vibration that characterized the motion of the ions with respect to the phosphate group of DNA, shown here schematically. They found that the frequency of vibration of different ions, they are observed in the low frequency spectra range from the 100 to 200 inverse centimeters, depending on the ion mass. And later, this theoretically predicted modes was also observed in the experimental spectra, which is displayed on the right on the slide. In the same spectral region, the conformational vibration of DNA also observed, and they associated with the displacement of the atomic group. These modes highlighted in the spectra, but I will not focus on them now. But additionally, you can see here in the experimental spectra a broad band that centered at about the 180 inverse centimeter, which associate with the bulk water vibration. And usually the experimental samples, they are highly hydrated, and therefore it becomes difficult to separate the vibrational modes of water and ions that are bound near the DNA surface. Nevertheless, the known experimental data for bulk water show that in this spectral region, below 300 inverse centimeters, the translational vibrations of water molecules are observed, and the low frequency water spectra can be present schematically as following on the slide. And in this spectra range, there are several vibrational modes can be distinguished. This includes the modes associated with the hydrogen bond bending near the 60 inverse centimeters, hydrogen bond stretching, including the both symmetrical and asymmetrical stretch with the frequencies around the 110 and 160 inverse centimeters. And also there are some specific modes like torsion mode, which is associated with the bifurcated hydrogen bond at about observed at about the 80 inverse centimeters. And also there is the mixed translational rotational mode at about 220 inverse centimeters. So for the further studying the dynamical features of the hydration shell, in our previous work, we studied the effects of various metal ions on the dynamics of hydration shell of DNA. So since we are all interested in the modeling, I'll go a bit deeper into details to the simulation protocol. we performed the classical all-atom molecular dynamics simulation for the 10 different systems. 5 of these systems contain DNA, metal, counterions, and water, showed here in the slide, in the animation, which is not moving anymore, but still. And the other 5 systems had only the water and metal counterions without DNA. The DNA fragment was presented as the fragment of 24 base pairs long with the following sequences, and it was placed in the cubic water box at about the 100 angstroms per site. The salt was added in the concentration at the 0.1 mole. And here we use the 5 alkali metal ions, different ions. It's lithium, sodium, potassium, rubidium, and cesium. So for the simulation, we use the GROMACS package, and water model was tip 3P. We use the force field amber PAMB C1 for DNA, and the temperature in the system was kept at 300 kelvins, and the pressure was kept at 1 bar. There was several equilibration, but in general, the production run was 100 picosecond, and for further analysis, each second of the production run was served as the starting point for the short 100 picoseconds in the INVI ensemble. So to analyze the obtained MD trajectories and study vibrational dynamics of modeled system, we firstly computed the absorption spectra, which can be then directly compared with experimental vibrational spectra. So the absorption spectrum can be obtained by performing a Fourier transform of the correlation function of the time derivatives of the total dipole moment of the system as following. Here the F omega is the frequency dependent prefactor, which is present in the following form, and the total dipole moment of the system includes the contribution from all the system elements. In our case, it's a DNA, ion, and waters. In principle, the dipole-dipole correlation function includes both after correlation terms such as water-water, ion-ion, and DNA-DNA, and also the cross-correlation terms such as water-DNA or ion-water. However, since our goal was in this work, our goal was to study the individual contribution of each component. We focused only on the after correlation function in the following form. That is, we computed the spectral contribution from each subsystem independently, and the cross-correlation terms in our case were neglected. So this simplification enables to a clear interpretation of the distinct vibrational features of the water, ions, and also DNA. So here on the slide, you can see the results that we computed for the DNA in the system that contain different counterions. And here under the graph, you can see the arrows that indicate the region where the characteristic vibration of DNA atomic groups are observed in agreement with the based on the experimental data. So our analysis revealed that in general, the type of studied counterion does not significantly influence the vibrations of DNA with one notable exception. As always, it's lithium ion. And in the presence of lithium, we observe the changes in the spectral region, which is associated with the DNA backbone vibration. So to understand this effect, we calculated radial distribution function, which I will not show you, but still. So we calculated radial distribution function for the lithium, all the ions in the system with respect to the phosphate groups of DNA, and our results show that a predominant binding of the lithium ions to the oxygen atoms of the phosphate group of DNA compared to the other studied ions. So this result is consistent also with the previous simulation studies of DNA with counterions that I showed you before in the introduction. We also calculated the absorption spectra for studied salts and obtained result. They reveal the quantitative difference between structure-making cations and structure-breaking cations. So spectra of the salts of the structure-breaking ions show three distinct absorption band, while the spectra of the structure-breaking ions show only two absorption band. And we also compared our results with the available experimental data, and our comparison showed the good agreement. Also, we analyzed this band is about 180 inverse centimeters, which is observed in the case of all calculated spectra, and the analysis showed that this band it corresponds to vibrations of the chloride ions that is also consistent with the experimental results. However, in this step we faced a difficulty, and the problem is that since ions are point charges, we cannot separately evaluate the individual contribution of cations and anions to the resulting spectrum. Therefore, to analyze the specific vibrational contribution of studied ions, we also computed the vibrational density of states. The vibrational density of states, it describes the distribution of vibrational modes over the frequency spectrum, and it can be obtained by the calculated velocity autocorrelation function of the studied ions, and we can then extract the vibrational frequency by applying the Fourier transform to this autocorrelation function in the following form presented on the slide. So we obtained the video spectra for ions, which is located in the bulk solution, which is shown as a black dashed line near the phosphate group, which is shown as a green line, and also in the major and minor group showed as a yellow and orange line. Here you can see the result for the structure-making ions, and here in the bottom the results for the structure-breaking ions. So the results show that for ions that located near the DNA, the spectrum shifts toward the higher frequency, with the most pronounced frequency shift, which is observed for the ions in the minor group, and this effect is mostly noticeable in the case of the structure-breaking ions. In contrast, the structure-making ions show almost no noticeable frequency shift. However, in the case of the spectra of lithium ions, which is located near the phosphate groups and also in the major group, we observe the band at around 820 inverse centimeters, and actually you can see that this band is absent in the case of the bulk solution. So this band can correspond to the vibrations that involve the lithium ions and phosphate groups of DNA, which is known as iron phosphate vibrations. We also analyzed the vibrational dynamics of water molecules in the hydration shells of the ions that are localized in the different region of the DNA, and compared these results with the spectrum of just a pure bulk water, which showed as a black line. So this data that I presented now, this corresponds to the structure making ions, and our analysis revealed that the vibrational spectra of water are shifted towards the higher frequencies, with the most pronounced shift observed in the case of the ions which are located in the minor group. Additionally, what is important and interest that we observe the isobastic point that appears at about 70 inverse centimeters. There are similar results we obtained for the water molecules around the structure breaking ions, and we also observe the isobastic point. So here we face a question: why do we observe the isobastic point in the all calculated spectra? And to address this question, we analyze the vibrational modes of water in 3 different environments: in the bulk water cluster, the cluster of bulk of water in the bulk, in the hydration shell of ion, and in the hydration shell of ion, which is located near the DNA surface. So here is blue arrows. They indicate the characteristic displacement of water molecules within the water cluster. So in the case of the water that located in the hydration shell of ions, the ions, as we know, the ions in the solution, they influence the structuring and dynamics of the surrounding water molecules, but still they allow them to perform the certain motion. But near the DNA surface and within the confinement region of the double helix, such a minor group, the motions of water molecules, they become significantly restricted. And in this case, the intensity of the translational vibrations of water molecules, it decreases, while the intensity of rotational motions, it increases. And this effect is, as we can see, is most prominent in the case of the minor group of the DNA double helix, and as a result of opposite changes in this mode intensities, we observe in calculated spectra the isobastic point. So telling shortly, the isobastic point indicates that due to the confinement of DNA and also the surface of ion, the translational vibration of water are more restricted, while rotational become more intensive. So here I'm going to finish with the some brief take-home messages. So the understanding the structure and dynamics of ion hydration shell around DNA, it's essential for elucidating the conformational dynamics and biological also functions of macromolecule. Due to the unique interaction the water molecules and ions in the hydration shell undergo with the DNA surface. Also, the properties of water molecules and hydration shell, they differ from those in the bulk due to the perturbation induced by both the DNA surface and surrounding ions and the presence of the macromolecule and counterions that significantly alters the water dynamics, affecting their hydration bonding behavior and potentially influencing also the structure and functioning of DNA. And as we can see, the molecular dynamics method can provide the valuable insights into behavior and interaction of water molecules in the DNA hydration shell. Indication our understanding in the DNA-related process in the living cell. So sorry for this mess talk, and thank you for your attention and patience. And also, I don't know if it's still needed, but I want to give you some exercises. I hope it's a simple exercises. I'll provide you the file with the normalized velocity after correlation function, from which you could calculate the video spectra to see how it looks like and answer some interesting physical question. So later, if needed, I will provide this file, that file with after correlation function, and also these slides. Thank you.
Okay, so thank you, Tetiana, for this very nice talk. Are there any questions from the audience from Kiev?
Are there any questions? Actually, Tatiana defended PhD thesis a few months ago here in our institute, and we know this material very well, and probably we do not have right now questions. So maybe in Zoom.
Okay, from the Zoom. Francesca, do you have any question? We cannot hear you again. Francesca, we cannot hear you.
First of all, a comment. Thank you very much, Tatiana, for this very nice talk, very visually appealing. I like very much your style, so thank you. It was not messy at all. I have some curiosity. So this behavior of lithium, the peculiarity is really very interesting. And I wonder if you thought about a possible biological role, if this can be connected to possible biological role of lithium.
Actually, I cannot say that there is any biological role of lithium ions because it's not physiological ion. It's a toxic ion, actually. And it's useful for the, just the experimental studies to see what changes, in this case, in the spectra, for example, to see the changes in the structure of DNA that can be induced by this ion. But I cannot answer this question about the biological role because I think there is no.
But still, for example, lithium-based medicine are still very important medicine for psychiatric treatment. And I mean, even if it's not an essential mineral, I believe it can be functionally important in because lithium-based medicine are very important. So who knows if this behavior could be somehow related. So I don't know. Maybe it is. Another question is a curiosity. Maybe you explained, but I did not. I am not sure I understood. So water molecule have three atoms, and in the vibrational analysis, there is a component that is for the torsional motion, which involve four atoms. Can you tell something about this torsional component of the water vibration?
Actually, I'm not sure that I can correctly answer this question because I never thought about it.
No, Tatiana. The question is torsional motion. This is.
Torsional.
Yes,
Sorry,
yes.
I
The
start to
mode of
talk about.
torsional vibration. You have a figure.
Yes, sure.
Yeah.
I don't know why I started to thought about the angle. Sorry. Okay, about this torsional mode.
Yeah.
So there are several studies that are explaining these modes. Stop me if I'll start to say some stupid things. So yes, there is several works. For example, here I present the schematical spectra that I took from this reference where they fit the spectra based on the theoretical some predictions. And there is one work from the Wallraffen that's let's say studied, but I'm not sure that it can be said that it's a experimental observation, but still it's more like a theoretical prediction. So they thought that this mode is related to reorientation of water molecules. As I told you previously, when water molecules reorient or rotate, so it can form this bifurcated bond with other water molecules in the cluster. So, and this mode they also distinguish this mode. I don't know how to explain it properly.
So it's like the one hydrogen is blocked in the bifurcated mode, and the remaining part of the molecule rotate around it.
Yes.
Yeah, something
Thank
like
you.
this.
Thank you.
And Francesca, I would like to remind you about your questions that you asked me yesterday. So probably Tatiana can say a few words about the slide. Tanya, please show the slide where you show the spectra. Yes, no, this one. I don't know why the reference is Thomas and co-workers. This is original result by Tatiana. So and this
is because of the these arrows with the region of DNA.
Yeah, so this gray region, it was yesterday the question. Can you comment this region?
Yeah, the difference of lithium with the other.
So this region is just highlighted to show you the only one modes where we see the it's not a shift actually, but it's like more the broadening of the observed peak in the case of lithium. So in this case, we fitted this region of the which we observed the difference, and we saw that this broadening appears because of the difference of the intensities of the modes, which is related to the phosphate vibrations of the DNA. So yes, then we. Do you have the specific question? So
No,
I
I
will
mean, I
know.
wonder, is this so lithium bind to the phosphate? So is this coherent with the fact that it becomes like part of the phosphate and makes it heavier, or because lithium goes in the phosphate in the hydration shell and the stick there? And I wonder if it's the phosphate it's coherent with the phosphate becoming heavier or
Yeah, it
not,
could.
or it cannot be related.
I think it's related to this ion phosphate vibration, and the main thing about the lithium ion is that it has the tetrahedral hydration shell, and it could be, and we saw that the one oxygen atom of the lithium hydration shell, it replaced by the oxygen atom of the phosphate group. So it became some strong interaction between. So I guess, yes, it's related to the, how to say it, both vibration, the lithium with the phosphate group.
Well, in simple words, I think we can say that the phosphate becomes heavier, but this is not only the effective increase of mass of the phosphate group, but also this is the influence of lithium on oxygen atom, and we have also additional interaction making influence the vibration of PO modes. And you can see in this region higher than 1000. So this is anti-symmetric OPO vibrations, and lithium influence these vibrations, and we see this influence. So
Thank you very much.
Thank you, Francesca. Thank you, Tetiana. We have also one question from the students. So from Zhiginta Murnikova, she said, thank you for a great presentation. A question from a technical part. How did you decide on the tip 3P water model? Would using, for example, tip 4P? What about the tip 4P? Maybe it's better for this case for hydration, or you just found that tip 3P gives you satisfactory results in comparison with the experimental data.
So thank you very much for the question. It's a very good question, actually. No, to be honest, tip 3P water molecules is pretty bad. And if I showed you the spectra which we obtain infrared spectra for this water model, you can see that there is no the band which associated with translational vibration of water molecules. There is no this band in our spectra that we calculated, but it's present in the experimental data. Why this happened? It's simply because that in the case of this band of the translational vibration of water molecules, it's very important to use the polarizable force fields. So, shortly answer to your question, we use tip 3P because it's the recommended water molecule for the force field that we used. But in general, to provide these calculations and do it more precisely, you should use the better water molecules, and this should be polarizable water molecules. I hope I answered to your question.
Yeah, I think PARM BC00 is developed with tip 3p. So it's recommended to use with this model. But in your case, it's better tip 4p. So you have to find a balance between these two observations. Okay, so
Yes.
anyway, Tetiana, thank you.
Thank you.
And are there any other questions?